Okay, so we have the question, what does all this have to do with the gradient? Now, on the last clip, you noticed that I corrected this slope. It should be negative x over 2 square root of c minus x squared, which is positive. X here is negative, and we know that the slope is positive, so just about everything I said about where we use the positive and the negative on this expression for the derivative was backwards. Just about. At least anything I said about the slope on this side of the y-axis. Okay, so that if x is on the negative side of the y-axis, if we're in the second quadrant, x will be negative, so that x is a negative number, and to get us positive slope we have to do the negative of x. So that corrects the sign, and in this quadrant we'll have negative slopes, and a negative slope on the lower part of the curve, the lower part of the ellipse, would be just x over 2 square root of c minus x squared. The x is already negative. That was simple careless error on my part, an error you got to be careful of. And that led to an inconsistency down here. Now let's just go through the calculation. The gradient is straightforward. We just do fxi plus fyj for the function we have here. The curve's x squared plus 4y squared equals c. The gradient of the function for which this is the level curve is 2xi plus 8yj. That holds for any point xy in the whole plane. If we're confined to this specific curve, then y, if we're confined, let's say, to the specific curve above the x-axis, the curve y equals 1/2 square root of c minus x squared, half of the level curve for the value c, then our y value is given by this expression. Now, the slope of a line parallel to the gradient vector is rise divided by run, j component divided by I component. That's 8y over 2x. As we say, y for this specific curve is 1/2 square root of c minus x squared, so that our expression 8y over 2x becomes, now this is written a little bit poorly, but it's 8 times the 1/2 square root of c minus x squared divided by 2x, and that simplifies. 8 times 1/2 is 4, 4 divided by 2 is 2, and we get this expression for the slope. Now, as we said before, the slope of a line parallel to in the direction of the gradient should be the negative reciprocal of the slope of the tangent line, since the gradient should be perpendicular to the curve at the point, perpendicular to the tangent line. And we see that this expression is indeed the negative reciprocal of this one. Okay, well, I don't have to point it out. If you look at this expression and this one, it should be very clear to you that this is the negative reciprocal of this. And that ties in this picture with the picture of the gradient, at least in the vicinity of this part of the curve. We haven't specified the value of c, so this is going to hold for any curve. Okay, and it certainly holds for a second quadrant point on any of these curves. We could do a similar proof for the first, third, or fourth quadrant, be completely analogous, and we would get the same result. The slope of the tangent line at any point of this curve, or the curve y equals negative 1/2 square root of c minus x squared below the axis, the slope at any point is going to be the negative reciprocal of the slope of a line parallel to the gradient. In other words, the tangent line is going to be perpendicular to the gradient. We can even go a step further and say that a vector, and let's make sure we got a tangent to y equals 1/2 square root of c minus x squared at a point x 1/2 square root of c minus x squared is, now this is just a vector, we could have any vector perpendicular to the vector we're going to get here. But if the slope is this, then you can think about why, but the tangent vector would be, I'm not going to call it T, I'm not going to call it R, what am I going to call it? Well, let's just say vector tangent equals I plus slope times j, which is x over, well, negative x over 2 square root of c minus x squared times j. Meaning that a unit tangent is t equal, well, this vector divided by its magnitude, which is the square root of 1 plus the quantity x over 2 square root of, and I don't really have room to write that in, put myself too close to the margin. That's your c minus x squared, and it's not c squared, it's just c minus x squared. Made a repair there. So we have unit vector tangent equals I minus x over 2 square root of c minus x squared j divided by, when we square this out, it becomes square root of 1 plus x squared over 4 times c minus x squared. And we could further simplify this. We could parameterize this curve in terms of a parameter t, parameter s, whatever parameter we want, and calculate a unit tangent vector. And it would come out either plus or minus this, depending on which direction the parameterization runs, counterclockwise or clockwise. Either the tangent vector here or the unit tangent vector here is going to be perpendicular to the gradient vector. If we take the dot product between the gradient vector and this vector, we should get 0. Now, expressing the gradient vector as 2xi plus value of y here, it's going to be plus or minus the 1/2 c minus x squared. And on the upper half of the curve, it's going to be the plus. So when we multiply that by 8, we get 4 times the square root of c minus x squared j on the curve x squared plus 4y squared equals c. Now you can write these expressions out and check for yourself with this vector and this vector, or with this vector and this vector. I'll just point to it. 2x multiplied by the 1, in other words, I component times I component gives you 2x. 4 square root of c squared, 4 square root of c minus x squared, j component multiplied by negative x over 2 square root of c minus x squared gives you negative 2x. So we get 2x minus 2x, which is 0, and we can easily verify that our tangent vector dot del f is equal to 0. Also, the unit tangent vector dot del f equals 0. And let's correct one more bit of careless notation. This is a vector.